Morning, everybody. So today we're getting started in on chapter 4, and we're going to start talking a little bit about how we name molecules. We're going to talk about alkanes and cycloalkanes today. We're going to talk about why they're useful, what they are, how do we determine and evaluate the fuel value of a hydrocarbon. We're going to talk about how we determine isomers of alkanes. I didn't ask you to bring your model kit today, but from now on, at least for the next 2 chapters, you need to be bringing your model kit to class every day, starting on Monday. So make sure you do that. And then we'll talk a little bit about naming, or as we call it, nomenclature. So how do we convert a structure to a name or a name to a structure? Okay? And that's going to take a lot of practice on your part. There is no way that we can cover all of nomenclature, nor do I expect you to understand all of nomenclature right now. We will get a lot of the nomenclature as we move on, okay? So we're going to just talk about the basics today. Now, in terms of alkanes, you all are familiar with things that look like this, especially if you drive a little further down south and into the areas where we do a lot of petroleum refining in Louisiana and in Mississippi, right? Really, that's crude oil, right? We're processing crude oil and getting valuable things from that. And so we'll talk a little bit about that today as well. So fossil fuels, you all are familiar with these. There's a barrel of crude oil. Does anybody know how many gallons are in a barrel without adding it up? 50's too high. It's 42 gallons per crude oil barrel, okay? Roughly 42 gallons, okay? And so most of the stuff that we get that's organic, that we use in organic chemistry, actually comes from a barrel of crude oil, okay? And so, for example, if you look at a 42-gallon barrel of crude oil, you're going to be able to get out of that about 19.7 gallons of gasoline. So just a little under half of a barrel of oil can be converted into gasoline. That does not mean that gasoline is sitting in that barrel of crude oil. It has to be processed, and that's what all those stacks and things that you see are. You have to put a lot of energy in to get a gallon of gasoline out, okay? And it turns out that that's not a energy favorable thing. We spend a lot more energy processing gasoline than we get out of it in our cars. It's an energy losing proposition, okay? That's why people are looking at other ways to propel your cars down the road that are a little more energy friendly. But gasoline is very convenient for us. You're going to get about 20 gallons of gasoline out of a barrel of crude oil. You're going to get about 8 gallons of diesel and home heating oil. We don't use a lot of home heating oil down here, but you move up into the Northeast and people outside their houses have these tanks that oil companies come and put home heating oil in, which is very similar to diesel. You're going to get about 4 gallons of jet fuel. Okay, so think about how many barrels of oil it takes for you to fly from here to wherever you fly to. It takes a lot of jet fuel to get you there, and you're only going to get about 4 gallons of jet fuel per barrel of oil. Okay, you're going to get about an equivalent amount of other things like lubricants, waxes, and solvents, motor oils, those types of things, the waxes that you use for a variety of substances. You're going to get about 3 gallons of what's called boiler oil. You're going to get about 1.3 gallons of asphalt and road oil. Think about all the miles of asphalt that you see, right? And a barrel of oil is only going to give you just a little over a gallon of that. That's not enough to cover this much space. So think about how many barrels of crude oil it takes to pave a mile of road. It's a lot, okay? It's an awful lot. And then in the last 1.5 gallons in this barrel, you're going to have what we call petroleum feedstocks. This is the stuff that I'm really interested in. This is the chemical products. This is the stuff that leads to plastics, medicines. Everything that we make out of organic chemistry pretty much so comes from this 1.25 gallons that's in that barrel of crude oil. Okay? And this is on average, depends on where you get your oil from, whether it's sweet crude or rough crude. But by and large, on average, this is kind of how you can break this down. Okay? Most of the money made out of a barrel of oil is actually in this 1.25 gallons. That's where all the expensive stuff is. Gasoline is cheap. It almost costs them more to make gasoline than they get out of it. Okay? So we think about all the gas and there's a big use for it. But this is where all the big money is up here in this part right up here, okay? Gasoline, kerosene, and diesel fuel, none of these things are pure products. So when you go and take your pump and you pump in gasoline into your car, you are not pumping in a pure compound. It is a mixture. And gasoline contains everything from pentanes to dodecanes. It's a mixture of hydrocarbons, okay? Have you ever heard of summer gas and winter gas? There's different blends for different times of the season, right? And they change the ratios of the hydrocarbons that are in there, okay? It's because if you have more of this high molecular weight stuff in the winter, your car won't start. So they put in more of this lower molecular weight stuff, so it'll start better. In the summer, it's exactly the opposite. You put in a little bit more of this higher molecular weight stuff. And I don't know how they play with the ratios perfectly, but pretty much so. They will blend that differently for different times of the year. Kerosene has anywhere from 12 carbons to 16 carbons. This is the home lamp oil kind of stuff that you use, right? If you have some of those old fancy kerosene lamps, or if you have a kerosene heater in your garage or your basement. A lot of people use kerosene heaters, right? You're burning hydrocarbons. Diesel fuel, much higher molecular weight than that. It's C15 to C18, various compositions. So the types of things that we use for fuels, right, really kind of coming out of this area of that barrel of oil, okay? And so the way that these things are refined, you have these columns. These are basically distillation columns. You guys are going to do a distillation in lab in a couple of weeks. You will use a column that looks nothing like this. This is an industrial size column, obviously, right? It's engineered to do this kind of stuff. But they bring in this crude oil, from ships and pipelines and whatever, and it gets heated in a heat exchanger, and it gets vaporized. And as it gets vaporized, it goes into this large column, and things that are really, really light and easy to convert into a gas come out the top. Okay, so things that have a boiling point below 20 degrees Celsius come right out the top real quick. This is that flare gas that you might see from time to time because they can't store enough of it sometimes, and so they just have to burn it off. Waste, right? I mean, it's just sitting there making a pretty flame for us to look at, but we're not using it for anything. And so flare gas is coming up here. Gasoline has a fairly low boiling point overall, or boiling range, I should say. I shouldn't call these points. They're not points at all. Gasoline will have components in it that have boiling ranges anywhere from 20 to 200 degrees Celsius. So gasoline will come off up here. Kerosene has a boiling range of about 175 to 275 degrees Celsius. It'll come off somewhere in here. Fuel oil, this is the thing like diesel and jet fuels will have boiling ranges of 250 to 400 degrees Celsius. They'll pull it off there. Lubricating oils, the things that you put in your engine or use to lubricate moving parts, those things have a very high boiling point, somewhere around 350 degrees and above, and they'll come out kind of down here at the bottom. And then the stuff that's the gunk, that's the road tar, that's the residue. That comes out the very bottom, and we just mix it with junk and pave a road with it. That's what we do. Okay, so you take that asphalt, of which we get about, 1.3 gallons for every barrel. They mix it with small rocks or actually even broken glass, and that's what they use to make your roads with, okay? And so it takes an awful lot of oil coming in here to make a mile of road. It takes an awful lot of oil coming through here to make your lubricating oil. We can get a lot of gasoline, we can get a lot of these gases, but the other things, it's really impressive how many barrels of oil it takes to make some of the things that we use every day. Okay, let's talk a little bit about combustion. All hydrocarbons undergo combustion. You all learned in general chemistry that a hydrocarbon gets burned into basically three components: carbon dioxide, water, and heat, right? We know that you're going to get carbon dioxide, water, and heat when we burn a hydrocarbon, okay? And that's assuming complete combustion, meaning we've got enough oxygen to completely convert it into carbon dioxide, water, and heat. If we have less oxygen, we can start getting things like carbon monoxide and other things like that. But we're going to assume, for the purposes of this class, we're going to assume complete combustion. It turns out that hydrocarbons, for the most part, this is about all we can do with them, is burn them or oxidize them. And that's why when we were talking about functional groups, we said that alkanes had very little function, and we really don't consider it a functional group, because basically the only thing you can do to it is burn it, okay, and get energy out of it. Not necessarily a bad thing, but that's pretty much all you can do with them, okay? You can have what's called the heat of combustion. You all should have done some calculations in general chemistry to get to the heat of combustion. Fortunately for you all, I'm not particularly interested that you can determine the heat of combustion of a hydrocarbon, but I am interested in your ability to understand fuel value in a hydrocarbon, okay? At least qualitatively, and that's what we're going to talk about. So if you take a mole of a particular hydrocarbon and you burn it with plenty of oxygen, you know you're going to get so much carbon dioxide and so much water. You should be able to balance that equation, and we'll have an example of that here in just a moment, okay? So let's look at a couple of common fuels. Methane. Where do you all use methane? It is natural gas, but what do we use it for, by and large? We use it to heat our homes. What else do we use it for? Cooking. How many of you have an automobile that runs on compressed natural gas? None of you, right? There are some cars that run on compressed natural gas, and there was a big push in the United States to convert more and more of our infrastructure into compressed natural gas, because compressed natural gas is the cleanest burning hydrocarbon that we have. Doesn't mean it's environmentally friendly, it just means it's the cleanest of all of them, okay? It gets converted quite easily. So if we take methane, 2 moles of oxygen, we're going to get a mole of carbon dioxide and 2 moles of liquid water, okay? It has a heat of combustion of 882 kilojoules per mole. But if we convert that into grams, it gives us 55.1 kilojoules per gram of energy. Now, most of us use automobiles that run on gasoline. Some of you may have hybrids. But for the most part, we're still a fossil fuel-based economy. Okay? Cars run on octane, right? So how many carbons would octane have? 8. Nowhere near 1 carbon with methane, right? So more carbon, we should get more energy, right? Absolutely, and we do. For every mole of octane that we burn, it takes 12.5 moles of oxygen to completely convert it into 8 moles of carbon dioxide and 9 moles of water. Okay? I just said 1 here, so I just halved everything. And in fact, when we burn a mole of octane, we get 5,452 kilojoules of energy. That's over 5 times the amount of energy that we get from burning a mole of methane. And so you're sitting there going, well, more energy per mole, great, it's a better fuel. Wrong. It's actually a worse fuel than methane, because it doesn't matter how much energy you get per mole. It matters how much energy you get per unit of mass. Okay? And in fact, octane only gives us 47.8 kilojoules per gram of energy. Why is it that I'm ignoring moles here when chemists pay so much attention to moles, and all of a sudden I'm starting to pay attention to mass when we're talking about fuels? Why is mass so much more important?
Moles aren't important because it doesn't really matter how many molecules you have. It matters how much you can do with a defined volume.
Okay. Heading down the right road. Think about it. Say you're designing a rocket ship to go to Mars. You want a good fuel, right? But you're going to start paying attention to it more on a per mass basis than on a per mole basis. And why?
The water you have, the more you can have.
Okay. Think about it when that rocket first starts to take off the launch pad. What's it got to move? Just the payload? It's got to move everything. It's got to move the payload and the fuel. That little bit of fuel that you need when you get to Mars, you've got to put a lot of energy into it right now to get that there, right? So I want a fuel that will give me a lot of energy per gram, so I have to have fewer grams to propel my rocket, okay? Yes, I get a lot more energy out of a mole of octane, but not on a per gram basis. meaning that I'm going to have to put a lot more energy in to move that gram of fuel than I'm going to have to put in to move a gram of methane. Okay? Now, there are engineering problems that keep us from using methane to do certain things, okay? I'm not talking about the engineering side of it. I'm just talking about from a pure fuel value kind of situation. We look at it on a per gram basis, which is a little weird for people to think about, because in chemistry we always think about molar ratios and stoichiometry, right? Well, we've got to think about that in terms of how we balance the equation, right? But we also have to think about it in terms of how much mass we have to move when we do this on when we're trying to consider a fuel. Okay? So let's do a little quick concept test. Take a minute. How many grams of water are obtained through the complete combustion of 1 mole of octane? So we have octane gets completely converted into carbon dioxide and water. How many grams of water would we get in the complete combustion of that? So you fire up your car, you put just 1 mole of octane in it, and you drive down the road. How much water could you get to drink out the back end of your tailpipe? Whoops, I'm sorry. So we got how many moles of water are we going to get? Okay. And we know that the molar mass of water, right? You get 9 moles of water according to the equation above. So you're going to get 9 moles times 18 grams. You're going to get 162 grams of water out the back end of your tailpipe. How much is that in volume if we condensed it? $162 milliliters. That's right. On a cool day, have you ever watched a car in front of you when they're stopped and you see liquid water dripping out of their tailpipe? It's not because they're leaking water from their coolant system. It's because the combustion product going down the tailpipe has cooled enough, because it's cold outside, converted into liquid water, and it's dripping out the end of the tailpipe. That's why your muffler rusts. That's why your tailpipe rusts, right? Because water promotes rusting of iron and things like that, right? You can't stop it because you're burning a hydrocarbon. You're going to get water in the product. Okay? Let's talk a little bit about the shapes of alkanes. What's the shape of each carbon atom in an alkane? What? What shape is it? It's tetrahedral, right? Each carbon is tetrahedral because it's what hybridization? It's sp3, right? And so we have these tetrahedral carbon atoms that you can build with your model kit, right? And so if we wrote it out, CH3, CH2, CH3, we would say that it's a linear alkane, or a normal alkane, as a lot of people call them, but that's a misleading statement. We only say that because how we write the condensed structure, CH3, CH2. It looks like going straight across. But in reality, if I gave you all a bunch of tetrahedra and asked you to join the corners of all of them, it makes zigzag shapes. Okay, and so these so-called straight chain alkanes are actually zigzags. So there's pentane, right? Kind of looks like a bird, right? Flapping its wings, if you consider that the head. There's butane, there's propane, right? So you go from a V to a zig and a zag and several zigs and zags in pentane, right? So you get this zigzag geometry out of putting these tetrahedra together. Not all carbon atoms in an alkane are identical. We've already talked a little bit about this. We have primary, secondary, tertiary, and quaternary carbon atoms, right? A primary carbon atom is a carbon atom that is bound to one and only one carbon atom, other carbon atom. A secondary carbon atom is bound to 2 other carbon atoms. A tertiary carbon is bound to 3 other carbon atoms. And a quaternary carbon atom is bound to 4 other carbons. We talked about this a little while ago, right? So in this molecule, we have primary, secondary, tertiary, and quaternary carbon atoms within that molecule. They do give different chemistries, especially when we get to chapter 10 and start talking about the chemistry there. A tertiary carbon has different reactivity than a secondary or a primary. Okay? But in terms of their combustion, for the practical purposes of this course, you can just assume that they all get converted to carbon dioxide and water, which is ultimately what happens in an excess of oxygen in the environment. But you need to be able to identify primary, secondary, tertiary, and quaternary carbons, and you had to do that on the exam. You had to identify secondary carbon atoms on that molecule that I gave you, okay? You also need to know that there are different types of hydrogen. Wait a second, hydrogen can only have one bond. So aren't all hydrogens the same? No. It depends on what that hydrogen is attached to. If that hydrogen is attached to a primary carbon, we call it a primary hydrogen. If it is attached to a secondary carbon, we call it a secondary hydrogen. If it is attached to a tertiary carbon, we call it a tertiary hydrogen. Notice what is absent. There is no such thing as a quaternary hydrogen. Why is that? Carbon can only have 4 bonds, and a quaternary carbon is bound to 4 other carbon atoms. Therefore, you cannot have a quaternary hydrogen, okay? So we can have primary hydrogens, secondary hydrogens, and tertiary hydrogens, and we can have those all kind of different within a molecule. So here you can see primary, secondary, and tertiary hydrogens in that molecule that's up there quite nicely. And they have different reactivities, and those will come into play in later chapters. So you need to be able to identify the different types of hydrogen that are in a hydrocarbon, okay? Now, we've already talked a little bit about constitutional isomers. In exam 1, I gave you C3H80 or whatever it was, right? And you all had to come up with the number of isomers that you could have from that particular set of atoms. Same thing happens with alkanes. You have a certain number of carbons, you have a certain number of hydrogens. There are multiple ways in which we can put those together, right? And as you get up to like 20 carbons, all of a sudden you have hundreds of thousands of different ways to put those things together, right? It's pretty large. So obviously, really large molecules I'm not going to hold you to. But for small molecules, 5, 6, 7 carbons, you should be able to identify all of the constitutional isomers, okay? Your model kit is very useful. So how many carbons and hydrogens do I have here? I've got 5 carbons and how many hydrogens? And I've got 12. So it's C5H12. It is pentane, right? We've learned how to name that one. That's pentane. Can I make constitutional isomers of it? You bet I can. I can connect those atoms together differently. And I only need to know 2 rules. I only need to know 2 rules for a hydrocarbon. I need to remember that hydrogen can only have 1 bond, and I need to remember that carbon has to have 4 bonds, right? I can mix and match the atoms any other way that I want, as long as it gives a unique structure. That could be a constitutional isomer, okay? Your model kits are very useful here. You can build this. You can take atoms apart. You can put them back. You can connect them differently. It works a lot easier than trying to do it on paper, okay? Because you can actually hold it in your hand and see what's going on. What I always do when I'm looking at the number of constitutional isomers of an alkane is I always start with the quote-unquote straight chain alkane. I start with this one. I would put that together and I'd say that's 1 isomer. And then what I start to do is I start to take off pieces and move them other places to see if I create a new structure, okay? So for example, just to give you a little color coding here, if I took this CH3 group, this carbon atom with its 3 hydrogens, and I swap places with this hydrogen that's yellow, I get a different structure. I've taken the hydrogen off, I've taken the CH3 off, and I've swapped their positions, okay? So this hydrogen is now attached to this carbon, which is here, and this CH3 is now attached to this carbon, right, which is here. That's a different structure. That does not look anything like that. Will everybody agree with that? Is there any other way that I can do this? What else could I do? This one? With this one? So if I change this with this hydrogen, is that what you're saying? If I do that, I get the same thing. This one? I'd end up with the exact same thing. And I'd be able to see that in a model. But I can end up with this. How did I come up with that? Yeah, I took this hydrogen, right? And this. But actually, it's from this structure, right? I took this structure, and I took this. Oh, that's what you were saying? Okay, yes, I took this and this CH3, and I swapped it. That's right. And I got this molecule called neopentane. Don't worry about the naming of it yet. This is nothing more than playing with Tinker Toys. If you've ever played with Tinker Toys, that's what your models are. Okay? You could put those pieces together in multiple ways. Okay? Let's talk a little bit about nomenclature. Nomenclature is actually really simple in principle, but gets really complicated the larger your molecule is. So we're going to really focus on simple alkanes for right now. Okay, your book goes into a little bit about alcohols and alkyl halides. Right now, we're just going to focus on the alkanes. We'll get into the other stuff as we need to. Okay? We'll get into the other stuff as we need to. I kind of view this again like a foreign language class. You don't go into a foreign language class and just learn vocabulary your first year. You learn sentence structure, and you learn some conversational stuff, and you try to learn it as naturally as you can, right? So the same kind of thing is going on here. But the basic thing for nomenclature is these three parts. So you're always going to have a parent name that's going to tell you how many carbons you have in the longest continuous chain. Longest continuous chain. Very important that you have those three words memorized. Longest continuous chain. Okay? That's number one. That's going to be the parent. You're going to have a suffix. It's going to tell you what kind of functional group is present. For alkanes, the suffix is ANE. Kind of nice. Alkane, ANE. The prefix is going to tell us the identity, the location, and the number of substituents that are attached to that longest carbon chain. And when we put them together, we're going to have prefix, parent, and suffix. Prefix, parent, and suffix. Right now, the suffix is the easiest part for you because it's just A and E, because we're just dealing with alkanes. So really what you're going to have to figure out is this prefix business and this parent business. What does the prefix tell us? Tells us a lot. Substituents and where they're at. What's the parent tell us? Longest chain. Number of carbons in the longest chain, right? Good. If we have carbon substituents that are bound to the long carbon chain, or the longest continuous chain, we call those alkyl groups. Right now, that's what we're going to be dealing with. We're not dealing with alkyl chlorides or alcohols. Okay, so right now we're going to be dealing with alkyl groups. An alkyl group is formed by removing a hydrogen from an alkane. So for example, CH4 is methane. If I remove a hydrogen from it, it becomes methyl. It's an alkyl group. And we'll see that example here in just a moment. Okay? If I have 2 carbons on my alkyl group, it's an ethyl group. If I have 3, it's a propyl group. 4, it's a butyl group. Okay, so on and so forth. So we're going to remove the A and E ending and replace it with YL. So if we look at an example, clearly this green line is the longest continuous chain. How would I determine the longest continuous chain? What does that mean? What does continuous mean? Doesn't branch. Okay? The way I like to think about it is if I take my pencil or my finger, I can go through the longest continuous chain without ever lifting it. If I have to go, it's not a continuous chain. They're not all connected, right? So if I look at it, I've got 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Clearly, the longest continuous chain is here in green. Once you've identified the longest continuous chain, the easiest thing for you to do in terms of naming it is take your pencil and actually circle it. That's what I do. Just circle the longest continuous chain. Everything within that chain is going to be part of the parent name. Since there are 10 carbons there, what's the parent chain going to be called? It's dec. A and E because it's an alkane, but the parent is dec. So we've got 10 carbons. Everything outside of that circle that I draw is a substituent. This is 2 carbons and 5 hydrogens. It looks like ethane minus a hydrogen, so it's an ethyl group. It's an ethyl alkyl group attached, right? This is CH3. It looks like methane minus a hydrogen. It's a methyl group. So this is some kind of methyl-ethyl substituted decane. Decane is the parent, and it's got an ethyl group somewhere and a methyl group somewhere. And so the prefix is going to tell me where those substituents are located, right? Okay. So we got to figure that out. So this is why it's important to be able to identify primary and secondary hydrogens or tertiary hydrogens, because it changes the name of your group. So for example, if the alkyl group that was on that longest chain, for example, had the hydrogen removed from a primary carbon, it would be a propyl group. But we could imagine it being attached here by removing a secondary hydrogen group. Okay? That would give you a structure that looks like that. That's known as an isopropyl group. It's not the same. Okay, so you can have an isopropyl alkyl group, or you can have a propyl alkyl group, because different hydrogens were removed. It makes a difference here. Okay? So the first thing that you're always going to do is you're going to find the longest parent chain, and it doesn't matter. Do not get in the habit of thinking that these read like a sentence, left to right. It's the longest continuous chain, period. It doesn't matter whether it's left to right to left, up to down to up. Doesn't matter. Or zig to zagged. It doesn't matter. You find the longest continuous chain. Okay? It doesn't have to be straight across from left to right like you would read a word. Okay? So for example, if we're looking at this particular structure, no matter how we go, the longest continuous chain that we can get is 8 carbons in that chain. Okay? And it just happens to be directly from left to right here. Okay? Notice if we go up and bend, you only get 7 carbons. So this is incorrect. This is going to be some type of octane parent. Okay? So it doesn't matter. Again, so here you can have it bent all sorts of ways. It's still the longest continuous chain. So on an exam, on a homework, identify the longest chain and circle it, and recognize that it doesn't have to be from left to right, or right to left, or up to down. Okay? It's very important. Okay? When you have 2 chains that are of equal length, you are going to pick the chain with the most substituents as your parent. It's just a rule. You need to memorize that rule. Okay? So for example, in this structure, I can have a longest chain that goes like this, and I can also have a longest chain that goes this way. They are both, how many carbons? 1, 2, 3, 4, 5, 6, 7. They're both 7 carbons in both. Which chain is correct? This one, because it has the most substituents. That is by definition from the IUPAC. There's no rational reason to it. It's just a rule.
Substituents, you just mean like atoms that are not...
I mean everything that is not part of the longest chain. That is exactly right. Right? This one only has 1 substituent, and this one would have an isopropyl substituent. This one has an ethyl substituent and a methyl substituent. Okay? You're going to go with the chain with the most substituents. Okay? So this would be your longest parent chain. Since it's 7 atoms, what would the parent name be? Hept. It is a heptane derivative, right? And this is clearly going to be a methyl group, although they're not showing the hydrogens, and this is going to be an ethyl group. So it's going to be some type of ethyl-methyl substituted heptane, right? It's not going to be an isopropyl substituted heptane. It'd be incorrect nomenclature to do that. Okay? Once you've identified the parent chain, now you have to figure out how to number the carbons, because we got to know where the substituents are located, right? That's going to be in the prefix. Well, we can number, in this case, from left to right, but we can also from right to left. We have to know which way to number our carbon chain. Okay? And so you're always going to number your carbon chain to give the first substituent the lowest possible number. Notice here, if I go 1, 2, there's my first substituent at carbon number 2, right? Here, if I was to go, it would be 1, 2, 3. I would get to my first substituent at carbon number 3. According to the IUPAC rules, we are going to give our substituents the lowest possible number that we can give them. So the numbering system on the left is the correct one. You're going to number this particular parent chain 1 through 8, going from left to right in this example. Okay? Now, if the first substituent is the same difference, or same distance, excuse me, from both ends, now we've got a dilemma. Right? If I look here, I've got 1, 2, 3, 4, 5, 6. Right? First substituent is at carbon number 2. Here I've got 1, 2, 3, 4, 5, 6. There's my longest chain. The first substituent is at carbon number 2. I can't make a decision based on the first substituent. Now we have to worry about the second substituent. And we're going to say, give that one the lowest possible number. Well, if I number here 1, 2, 3, the second substituent is at carbon number 3. But here the second substituent would be at carbon number 4. This is incorrect. It's this one. So basically what this is telling you is each one of your substituents should have the lowest possible number. If you can't make a decision on substituent 1, look at substituent 2. If substituent 1 and substituent 2 are identical, look at substituent 3 until you find a difference and give it the lowest possible number. Okay? Rarely will you have to go out past carbon 2 or 3 for this course. Okay? When numbering a carbon chain results in the same numbers from either end, assign the lower number alphabetically to the first substituent. So it doesn't matter if I number from left to right or right to left, I get the same numbers. Now you look at the alphabet. Okay? Notice here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Both substituents are on 3 and 5, no matter which way I number, right? But I think you all will agree that ethyl comes before methyl in the alphabet. So we're going to number from left to right here because that gives the ethyl group the lowest number and not the methyl group. A lot of rules, huh? Yeah, a lot of rules. A lot of rules. But trust me, the more problems you work, the better you'll get at it. Just like when you took your Spanish or French class in high school. The more you talked about it, the more you learn, right? So, this is going to be correct. The longest is 7. No matter which way I number, I end up with the same numbering system. The substituents are at the same numbers, but I'm going to have to go with this one because ethyl comes first in the alphabet. Right? I mean, organic chemistry is can you count to 10 pretty much, and do you know your ABCs? Right? That's really what this is all about. But remembering the rules. So what do you think is going to be good for your next note card for next time? Many of these rules that you have trouble remembering, right? You will get to remember these rules the more and more you use them. But on the exam, what I'm really interested in is can you use the rules, not so much can you memorize the rules. Okay? So if you have trouble remembering one of these rules, write it on your note card. I promise you by the end of the semester, you'll have it down pat. But for exam 2, maybe you can't remember what to do if the numbering is the same both ways. Write it down. Because what I'm interested in you being able to do is apply it, not memorize it. Okay? So, now we're ready to name name the substituents. Okay? We're going to name them as alkyl groups. So here we have a single carbon. It's got 3 hydrogens on it, which aren't shown. That's a methyl group. This is an ethyl group. This is another methyl group. So this is a molecule that has 8 carbons in the parent. So it's going to be an octane parent, right, with the A and E ending. And it's going to have 2 methyl groups and an ethyl group. It has 3 substituents. So now we're going to have to put the name together. Okay? And so when we do that, we end up with the name 5-ethyl 2,6-dimethyl octane. Repeat that for me. 5-ethyl 2,6-dimethyl octane. So what is this telling me? Notice the substituents are alphabetized. Oh, wait a second. D comes before E in the alphabet, right? We don't use that as part of our, just the alkyl groups themselves. Ethyl comes before methyl. 5-ethyl tells me what? On the number 5 carbon of the parent chain, I've got an ethyl group. Notice that numbers and letters are separated by hyphens. So 5-ethyl. 5, I've got an ethyl group. Letter, number, so I put a hyphen. 2, 6 tells me that at position 2 and at position 6, I have methyl groups. But I've got 2 of them. So I can't say 2,6-methyl. I have to say 2,6-dimethyl. If it's just 1, it would just be methyl. 2 is di, 3 is tri, 4 is tetra. Okay, and that's about as far as you need to go. Okay, but you can go up higher. So this is 5-ethyl 2,6-dimethyl octane. That's what the answer would look like. Very important that we use this type of nomenclature because this can be coded into a computer and a computer can read it and actually draw the structure. You all know you can get ChemDraw for free here at the university. If you don't, I'll have to send out a link to you. You can get it. And I'm not so sure in the version that we have whether it will go from structure to name or name to structure. I'd have to look at that. But the version that I have, which is the professional version, I can type in 5-ethyl 2,6-dimethyl octane and it'll draw the structure for me. Or I can draw the structure and it'll spit out the name for me because it's systematic. It's nothing more than interpreting a set of rules. It can be coded in a computer. Okay? So, let's look at this as an example. I give you this as a structure. What kind of structure is this? Bond line or condensed? Condensed. You all might be really good at naming condensed structures, but I stink at it. I cannot look at that and derive a name. I've been doing this for over 20 years, and I can't do that. So chances are, I bet you can't either. All right? You might be able to. Some people can. I cannot see the name from a condensed structure. But I don't have to. All I have to do is convert that condensed structure into a bond line. There it is. There's the bond line structure for that particular condensed structure. What's the first thing that I need to do to name it? I need to find the longest continuous chain. What is it? Six carbons. Or you could have gone, would have been the same chain. But I can't go because that is only 5 carbons. So what's the parent? It's a hex parent. It's a hexane molecule, right? So I've just circled it. What substituents do I have? I have a methyl group, yes, and an ethyl group, right? I can either number the green way or I can number the white way. And they're not equivalent. Which one are we going to use? The what? The white. Okay? But if I name it based on the green, I would end up with a name of 3-ethyl 5-methylhexane. If I named it based on the white structure, or numbering system, I would get 4-ethyl 2-methylhexane. And a lot of people make a mistake here, and they go, oh, wait a second, Dr. Masterson always said we have to have the substituents with the lowest numbers. Green is correct. No. Why is the white one the correct one? The first point, right? We get to the first substituent at carbon number 2. Here, the first substituent happens at carbon number 3. Has nothing to do with how they come in terms of the first letter here. It has to do with that first substituent. Okay? So we're going to finish up on this on Monday and continue on. I've got your exams. I'm going to hand those back. If you are interested in the exam redo, you have to pick that up. Today I have the exams with me, and so you can pick them up afterwards. I'll say your name, just raise your hand, and I'll find you.